Okay, great. So here we are with the correction of masterclass number 11 of this series. And we have here Omar Valson showing us how to do the exercises. So go ahead, Omar.
Okay, thank you, Johnny. So I'm going to go over let me first share this screen. So I'm going to go over the solution of this tutorial here on variation and sampling with PLUMED. And this basically, as I say, covers how to run variation and sampling with PLUMED and the VAS module in PLUMED. Okay, so this assumes that you have like a PLUMED with a GROMAX patch with PLUMED setup with the VAS module enabled and GROMAX compiled using the MPI library. And this has been tested with version 2.8 of PLUMED and GROMAX 2020.6. And you can follow this link in the tutorial how to get the code. And all the files are here in this GitHub library, and which you can just clone from this GitHub repository. And here I just started with a summary of the theory, but this was covered in the last lecture, so I will not talk about this today. So we're going to look at a very simple system, which is just the association and dissociation of sodium chloride in water. In this case, we have a system of one sodium atom, one chlorine atom, and 107 water molecules in a box. This is a rather small box to kind of reduce the computational time. So this means also that the cutoffs used are quite low compared to what should be used in production runs. So this system should not be used in production runs or do any kind of real simulations. Okay. Still, the system takes a bit of time, so the runs have taken around 10, 15, 20 minutes to run on a laptop using 2 MPI processes. But this can, of course, be reduced by using kind of cluster. Okay, so the most relevant CV version you can think of the system would, of course, be the distance between the 2 atoms. And this is just defined in this collective variable here. And we can also look at the solvation of the atoms. So this we define here using this coordination number collective variable, which is just the where we look at the coordination number of the sodium atom with respect to the oxygens of the water molecules. And as always, when we're using coordination number, we use like a kind of a smooth switching function to get smooth forces. So these are all pretty standard, should be pretty standard parameters. Also, to kind of limit the exploration of base space and CV space, we put an upper wall on the distance between these atoms. So we just put an upper wall at a distance at 2.6 nanometers with some given kappa. This is just to avoid having the system exploring too much the base space. This is, of course, just to kind of reduce the time it takes to converge the simulation. Okay, so we start by doing the simplest case, which is just biasing with one collective variable. This is exercise 1. And yeah, so every VAS simulation has like 3 key ingredients. So this is like the basis set, target distribution, and optimization algorithm. So this, let me see. So this is the first, from the first exercise, the PLUMED input. As before, we just define the collective variables here. And the first thing we do is that we use the so-called wavelet basis set to expand the bias potential. So this here, we define the basis set for the first collective variable, or the only collective variable in this case. So here we use these wavelets. We use so-called simlets, which are as to say a more symmetric version of the wavelets, which we found to observe to be perform better. Order is just the order of the wavelets. 10, this is something which you should not really need to think a bit too much about. Order of 10 is reasonable to use. We found out using order of 8 to 12 gave reasonable result. This is something related to the smoothness of the wavelet basis set. And you can see further information about this parameter in the paper describing the wavelet. A more important parameter is the number of basis functions, which is just the number of basis functions that we used in this given interval. And as for all basis set or basis function within variation and sampling, we need to define the minimum and maximum of the basis set. So this is defined in these two keywords here. And this tails threshold is basically telling us how many edge wavelets we should include. So in this case, we include all wavelets that are yeah, okay, maybe I'm not go too much in detail with this parameter. This basically tells us like if you have a wavelet that is slightly outside with the maximum outside the edge of the range of the basis range, then you include all wavelets that have a value which is at least 1% of the maximum value. So this is just basically how this determines a bit how many basis functions we obtain. So this is yeah, but as I say, this further information about the wavelets you can read in the paper. So then the target distribution, in this case, we use a well-tempered target distribution with a bias factor of 10. This is just defined here. So you define the basis set and the target distribution just in this kind of actions here. And then you use this action here, where's linear expansion, to define the linear expansion of the bias potential. As with any bias, you give the argument of the collective variable in this bias. And then here you define the basis function that you should use within this bias. So here we define the label BF1, and we use that here. And the same with the target distribution, we use this, define the target distribution here. And then we just define the temperature as we normally need to do, although in many cases this can be automatically detected by the code. And this grid bins is just telling us how the grid that is used for various grid inside the code, which are used to do some integrations. Normally a value of 200, 150 to 200, 300 should be fine. This should not affect the result in significant ways. So now we have defined the basis for the bias potential here. So now we then finally defined the optimizer. And in this case, we use this average stochastic gradient descent that I talked about last time. The theory is also in the tutorial about this optimizer. And here we need to define a few parameters. The stride is how often we update the bias potential. And this is given a number of empty steps. So 500 means that we update the bias potential every 1 picosecond. And this is normally a quite reasonable value. Because here we have a time step of 2 femtoseconds. So the step size is basically like how much we change the parameter in each step. It's iteration. This is something sometimes called the learning rate in machine learning algorithms, stochastic optimization algorithms. And then we define here how often we update the target distribution, because this target distribution is going to have to be iteratively updated. And this tells us how often we update the target distribution. Then there are these various output parameters, which is basically how often we output various files during the run. So here we output like the phase every 100 bias iteration, the bias potential every 1,000, the coefficient every 10 bias iteration, and etc. And then you just have the normal upper walls, and then you have also like just the print statement with the various parameters. So it's explained. So this is basically the input file. Is then explained in the tutorial how to do this run, and that is basically first in the generated TPR file, and then you just run GROMACS using the scripts which are given. In this case, I've already run all of the simulations because they take a bit of time. So we can just look at a bit at what we get out from the simulations. So we get out the various phase files. This is just the fringe surface at various iterations. It's like it's given by, they are always labeled by the iteration number, and this is determined by this phase output parameter. And then we have, and these are just like normal phase files given by PLUMED. And then we have also like the output of the target distribution and various other parameters. And also what we have here in this file, this coefs.data, is basically the coefficients from the run. So they are given in this format here. So this each field here is correspond to a given iteration, and you can see how this kind of coefficient change during the run. So, and they will kind of converge to some given value. And I will show this better way during the in the Jupyter notebook. So this is basically how it works, what you get out. So pretty standard, and also you get like the bias out. But we will visualize this now. So say we have assumed that we have just run the simulations. So now let's just start by analyzing the simulations. So I do this in this Jupyter notebook, which is in the GitHub repository, both using kind of which has already been run through all the cells, and also which is something which has been not, which is kind of a clean run. So we just use NumPy and matplotlib to plot. So this is just what we need to import. Okay, and here we just to give everything out in units of thermal energy. Here I just define kBT at 300 Kelvin. Okay. So as I say, the exercise 1 was just to passing with one collective variable, and it's assumed that the exercise has already been run. So the first thing when you look at the simulation, the same thing as when you're doing any kind of type of simulation, is just to visualize the time evolution of the collective variables. So this, in this case here, we can see the time evolution of the distance of between the sodium and chloride, which is the collective variable that we're biasing. And we can see there's a pretty reasonable kind of diffusive behavior between in this range. And we can also just look at maybe the first 100,000 picoseconds. And then we can see that it seems to be pretty reasonable and diffusive in CV space. Like after like 500 picosecond, it's more or less diffusive. And this is what we can see here. We can also look at the kind of the coordination number, or which determines the solvation of the sodium atom. And this is like, is reasonably diffusive, although this is not biased, but there is strong coupling between the distance and the solvation, as we see below. And here we can also just see the coupling between these two collective variables. We can see that they are quite coupled. So like for distances of small distances, which is reasonable because of course when they get closer together, there is not as many water molecules that solvate the sodium atom. Okay, so first thing, let's look at the time evolution of the coefficients. This is like these coefficients. The coefficient file directly is not really quite convenient to like visualize the time evolution of the coefficients. And one thing which I didn't mention is that in this file you have two sets of coefficients. The first, this is just here. This line here is just the exact number of the coefficient. While here, this is the coefficient, the so-called average coefficient, which are used in the bias potential. While here is the so-called instantaneous coefficient or parameters. But this was discussed in last time how the optimization algorithm works. So it has this like instantaneous parameters and average parameter. And the average parameter are used in the bias potential itself. But as I say, so to get the time evolution, we can just do this here on the script here. This is like a script which is given by the given in the tutorial, and you will get this code, this coaf different file for different coefficients. So now we can basically look at the different coefficients. So this just plot the different coefficient, and here we always have like the that the orange line is the instantaneous parameter, and the blue line is the average. Okay, we can see here, for example, for coefficient 1, this is still going down. It doesn't seem to be converged. But this is not an issue, as I will see in the next, when we look at the fringe surface itself. It's the same with coefficient 2. And here we start to see something which is slightly better behaving. And if we go to the coefficients, like coefficient here 6, this is something which seems to converge much better. And the same with coefficient 7. The reason is that these coefficients are low, because these are the coefficients for the wavelet basis set, and the wavelets are localized basis functions. So this coefficient, the first few coefficients are the coefficient for the wavelets on the edge, on the edge of the bias. So this is something which is like, so you would, and as we see during the when we look at the pairs, this is not converged because we have not explored that area very well, because of the distance really cannot really go into these regions. But if you look at the coefficients, which like coefficient maybe 9, we can see a better convergence of the result, although the instantaneous one fluctuates a lot. But this is something which is reasonable and happens. And these coefficients like 10, this is more in the middle of the simulation. So we can see there's different coefficients. And so the convergence of coefficient seems to be reasonable in this case. Okay, so let's now look at something which is more interesting and look at the convergence of the fringe surface. So during the run, we get the fringe surface at different number of iterations. So to look at the convergence, you should look at how the fringe surface at different iterations compares. And the fringe surface that we get out from the simulation is always aligned such that the minimum is at 0. So here I'm just comparing like different iterations. So this is just for loop over different iterations. And let's start by looking at from like step 500, from 500 picosecond to 4000 picosecond in the steps of 500 picoseconds. So you can see here how it converges. So you can see here that after let's say 1000 picoseconds, the different profiles are pretty in good agreement with each other, in reasonable agreement with each other. The one on 500 is slightly less, but this is kind of reasonable. And here we can see why we are always like with this kind of coefficient at the edge, why they're still changing. And this is because this is a region that we have not really explored so much. if you look at the time series of the bias CV, you can see that we never really go down to 0.2 or really up to 0.7. So we could maybe redo the simulation if we wanted with a reduced range of the bias potential to kind of have a more nicer behavior here at the edge. But in reality, this doesn't really matter. This here does not matter so much. So what we are more interested in is the behavior within this range here. Yeah, so this is just like, if you look at like the convergence from the beginning to at the end. So now to maybe further look at the convergence, let's look at the convergence of the last 1,000 picoseconds, the last nanosecond. And here we can see, if we look at it as in steps of 100 picosecond, we can see that the profile is pretty well converged. So we can see that the fringe surface has converged here pretty well. Another way to look at the convergence, which is of course a common way to look at the convergence, is to look at the fringe difference itself. So here we just look at this at the fringe differences. To determine where we do the calculation of the fringe difference, we should look at, let's say, the probability. So here I just plot the probability instead of the fringe surface. So we can see here that if we look at this probability here, we can see here around below 0.36, we can see that this is the associated state. So, and here below above 0.36 nanometers is the dissociated state. So we can see here that if we look at the fringe, the difference between this associated state and this dissociated state, we should take the integration range from the split integration range here at 0.36. So in this case, we basically just need to integrate over the probability of these regions and compare it to this region. This is a pretty standard just fringe difference calculation. So I just did this here. We define kind of a function to do this calculation of the fringe difference. And we just need to define the location where we kind of separate the two regions. And here we just add to the probability of A if we're in this region and B if we're in this region. So this is like a pretty standard calculation of fringe difference. So, and this is what we do here. So this is just to calculate the fringe difference for the different fringe surfaces as a function of time or iteration. And this is what we get out from this run.
Sorry, Omar, can I ask a question on this? So here I see that you are showing the as a function of time the free energy difference. That's estimated from the bias.
Yes, directly from the bias.
I see. So in theory, there is the same caveat that you have with well-tempered metadynamics. It could appear to converge just because by choosing the parameters of the gradient descent, the bias could stop changing, but there are no transitions, right?
Yes, but I mean, of course, yes, that's true. Of course, as to assess convergence, the first thing is to look at always the time series and make sure there are transitions. And we could see in the time series there's a lot of transition between the two regions. So that seems to be fine in this case. But yes, meaning you really need to make sure that that there is transitions between like two regions. That it doesn't. If there are no transition, of course, it will not really make sense to go forward to look at the convergence.
Okay, thanks. And then another comment on those probability distributions. So one of the two peaks, of course, is affected by the size of the box, right?
Yes, yes, and also the wall. Meaning we have a wall at 0.6. So I mean, it's not the right description of the association, because we have a wall, so that will of course compress the range, reduce basically the entropy of the, and so we can just think of this system as the association with this given wall. It's true that this is not really the right, probably it's not really the right description of the system, because we have this wall acting on the system. We could, for example, try to increase the range of the bias and the wall a bit further out, but in this case I decided to have the wall at this level. But yes, I mean, of course, this is of course affected by the size of the box and also like the location of the wall.
Yeah, but I think we have in another masterclass probably the explanation of how to integrate this correctly.
Yes,
because I think there is another exercise which is similar with the.
In principle, you could also during the rebating, you could rebate this wall away. I didn't do it in this case just to have, because I want to compare exactly with the fringe surface from the bias, but in principle you can semi-correct it by looking at the like during the rebating, take the wall into account. But of course the statistics in the range beyond this will be not good, because the sampling is, you don't really sample that region.
Yeah, thank you.
Okay, yeah, so we see here that it's a reasonable convergence of the fringe difference, as you see here. Okay, so what we can also look at is that so far we looked at the convergence of the fringe surface, and in this case the fringe surface is obtained from the bias potential and the target distribution. This is given in this this equation here. So basically the fringe surface is given by the negative of the bias potential plus the negative of the logarithm of the target distribution. Okay, so we just look at this case. It's per se this is not something which you might normally look at, but let's just look at in this case how it converges. And since these things two are related, they converge in a kind of a similar way. So we can see here that the bias potential is pretty well converged in this as they run very quickly. And we don't have as much output of the bias potential, so I show it only with the step size, only like every 1,000 picoseconds. And also we can look at the convergence of the target distribution. As I say, that is iteratively updated according to as discussed in the tutorial and also in the relevant paper. And that we can see that the target distribution converges. We can also see here there are some active effects, but they don't really matter at all, because in this case the CV is not explored in this region. This is why we have, let's say, some active effect. We could reduce the range of the bias potential to reduce it, but this is not, doesn't really matter so much. And also, yeah, we can also look at the negative logarithm of the target distribution, and this converges in the same way. And here we can see already something which we discussed in the lecture, is that as here we are using a well-tempered target distribution. We should be like that. Effectively, we're sampling an effective fringe surface where the barriers have been reduced by a factor of gamma. And in this case, gamma is around 10. Gamma is 10. And in this case, the barrier, if you look at the fringe surface, is around 5 kBt or thermal energy. And we can see here in this negative logarithm that this is also 0.5, which would correspond to that we reduce the barrier by a factor of 10. So this is basically, so this is just the negative logarithm target distribution. For most cases, you will not really be looking at this, but it's just interesting for the system to at least look at this briefly. Okay, so now we have looked at the fares obtained directly from the bias potential, but now we can also look at obtain it through rebating. Okay, as I say, we can always look at we can always do rebating for bias sampling, and here we generally do not need to take into account time-dependent constant, because there are no like time-dependent constant in the bias potential due to how the bias potential is constructed. But normally we are using just this umbrella style rebating, similar like as done in aerodynamics, and there we have the same issue that the bias potential needs to be kind of quasi-stationary. So, and if you look at, let's say, the bias potential here, we can see that, let's say, within after 1000 picosecond, the bias potential is more or less stationary. So probably if we would take, we would look at that, we would, we would see that we should maybe trim, let's say, the first 500 to 1000 picoseconds from the simulation. As I say, because in the beginning, the bias potential is changing a lot, so this can affect the rebating. So we should always trim the beginning of the simulations. So just to understand how much we should trim, it's good to look at the behavior of the bias potential. So we can see here, this is just the behavior of the instantaneous bias at each step. And then we can see that in the beginning here, within the first 500, the bias, we have some kind of peak here. And this is the case where the bias potential is changing a lot initially, and then it kind of equilibrates. So from this graph here, I would say one should probably ignore at least 500 to 1000 picoseconds from the beginning. We can also understand this better by looking at the weights, which are just like the weights that come into the rebating. And here I just calculate the weights, they're just the exponential of the bias potential. And here I just renormalize the bias with the maximum, just to have weights which like are highest one. So we can see here that we have a high weight here in the beginning of the simulation, while afterwards it kind of converges. So we might have an issue if we would, in this region here, in the beginning where the bias potential is changing a lot and the bias is not quasi-stationary. If we would include this region here, we might have bad result because there are few points with very high weights, while later on they cannot converge. So, yeah. And we can see most of the highest weights around here at small distance from the associated state. Here I'm just plotting like the weights as a function of the distance corresponding to each weight or each bias potential. Okay, so from this, we can see that we should probably trim around maybe 500 to 1000 picoseconds from the beginning. So let's just look at this. So let's now just do the rebating. So here is this rebating file that is in the simulation. It's basically like a simply just read in the color file, which we trim, and then you just do a histogram and convert that to pairs. This is pretty standard in PLUMED, and you can find this more information about this in other tutorials. Here we're using just a discrete histogram, but I will show later how to do a kernel density estimator for this result. So to kind of further check out how much we should trim from the beginning, let's try to do some results where we kind of trim different times from the beginning. So we trim basically from 0 to 1000, and we trim always, let's say, 0 to 1000 picoseconds, and we trim it in a step of 100. So this is just does the simulation, does the trimming for multiple times. There is this Python code given in the tutorial, which you basically here we open a color file, and here, so the color file here, and we output a new color file where the time has been kind of, we remove the first given number of, we remove all the files corresponding to up to a given number. So this is just a Python loop. And then we just basically do the rebating multiple times and we compare the result. So actually what happens here when this has finished running for the different cases, we can actually see here that even if we will not trim everything, anything from the color file, the results are very similar. So in this case, this initial high weights in the beginning did not seem to affect the result in much way. So in this case, it might have been okay to just not trim anything. But in general, you always need to trim something from the beginning where the bias is changing more. But it's always good just to look at how this behaves as a function of like some given times. So from this, we can basically say that we should basically trim, let's say, 500 picoseconds from the color file. And this is what we do here. This is just to get the final file. And now we can compare the fares obtained directly from the bias potential and from rebating. This is what we do here. So we can see that there are some slight differences between the two files, like the barriers maybe slightly not slightly lower, and also some small differences here. So there are some small differences between the bias and the rebating. Maybe this could be improved by running the simulation longer, or it could be that maybe the bias potential doesn't have complete flexibility to get the fares. But we also see later on, when we look at more other independent simulations, that this is that the bias for independent simulation and rebating, they more or less compare well with each other. This seems to be, this is a reasonable, I think this should be a reasonable difference, and this is within our like error bars. If you would maybe see a large difference between the bias directly from the bias potential and the bias from rebating, that could indicate there is something wrong in the simulations or it has not converged. But in this case, it's reasonable agreement. Okay, and as we can also do, we can also smooth the result using kernel density estimator. Here is what I did here. So this is just given the new plumed rebate.dat input, where instead of a discrete histogram, we use a kernel density estimator with Gaussian kernels. And this bandwidth is a parameter that I kind of have already optimized beforehand. So this is a parameter that gives some smoothing, but does not over smooth the result. Okay, and this is just comparison of the fares from kernel density estimator and from rebating. And we can see.
Sorry, just one question there.
Yes.
About the bandwidth of the kernel density estimation. Just how did you compute it? Is just trial and error, or do you have a method to get it?
I used, in this case, I used trial and error, let's say. I mean, there are some methods, there are, I don't remember the name, there are some rules based on number of samples. I mean, there are some rules for kernel density estimator which are available, like even in like Python machine learning framework, etc., that you can use to select the bandwidth. So how I have normally done it is that I do a bit of trial and error. Let's say, I look at results and see like if it gives some smoothing without over smoothing. Let's show example. Now let's go from 0.04 to 0.08. So we double the bandwidth. And now this has run again, and now we replot it. So you can see Now this green line is from the KTE. So we can see now it's a smoother line for sure, but now we start to kind of maybe not behave as well here in this region here, so it might start to over smooth a bit the result. So what I normally do is that I just do a discrete histogram, and then I do a bit trial and error with different KTE parameters to kind of check like when do I start to over smooth the result. I mean, there are of course more clever ways of doing it, and if we would maybe improve it, increase it even more. Then you should see this green line like has gone down. So we have here I started to over smooth the result too much. So in this case, this should be the parameter is too large. So I found that using a bandwidth of 0.004 gave reasonable result. But there are certainly more clever ways of doing it, and you can use some kind of cross-validation or something like that. But this is, in this case, it's kind of gives reasonable result.
Thank you.
So now we can also do another thing. We can rebate also on both the CV that are biasing and the CV that we did not bias, which is the solvation collective variable. So this is just done in this input here, where we kind of now we just do a two-dimensional histogram. We just need to define the range and the grids, and also the bandwidth. And this is a bandwidth that we kind of I got by trial and error before. So this So now we just run this rebating. And I pipe everything to dev null, not to have the output. Of course, there is some plumed output run here, but just to have a bit of cleaner result. So here, this is just to plot the two-dimensional plot of the two-dimensional phase, and so this is the two-dimensional phase here. And this corresponds well to what we saw before for the coupling between these two collective variables. So when it's bound, we have this like two solvation states, and when it's unbound, we have this like these two solvation states. So we can see that there is like a strong coupling between the distance between the ion pair distance and the solvation of the sodium. But in general, like the solvation degree of freedom is normally fast compared to this distance. So it should be normally sufficient to bias the distance to get good sampling. But later on in the below, we will do one of the exercise is to add also bias on another degree of freedom, or the solvation degree of freedom. Okay, so now this is also a good exercise to assess the convergence, is to run another independent simulation. And this is always good exercise, to run multiple independent simulations. And in this case, you cannot get, can compare the result. So this is basically what we do here in this exercise 2. And we just need to change the starting configuration. I gave 2 starting configuration in the files, so you just need to change that. Okay, so, and we're just doing everything the same, all the same parameters as before. First, we should double check that the time series is kind of diffusive, and this seems to be reasonable diffusive here in this case here, in this also for this simulation. Okay, so now we just do the same as before. So this is, let me see. Yeah, so this is just comparing the 2 different simulations, and we can see that they're exploring this similar phase space, and so they behave rather similar in the time series of the biased collective variable. Okay, now let's look again at the convergence of the Fringe surface. And again, okay, we can see here that is, let's say, it took a bit longer to converge, slightly longer to converge. Here we can see that the first 500 picoseconds is still a bit changing, and we can see here in this that is still changing in the kind of the last runs, but so it's behaves slightly different. Maybe it took a bit slightly longer time to converge, but we can also look at the last one nanosecond or last 1000 picoseconds, and here we can see there's some more variation than we saw for the previous case. That was what was here. This is the previous case, the last 1000 picoseconds, and we can see there is some more variations in the runs. But I think this is still okay. Okay, so now let's compare these two different runs, how the Fringe surface look from these two different runs. And we can see there are some small differences, but they are in a reasonable agreement with each other. So this can just be kind of some small fluctuations. And in this case, we should like maybe run a few more runs to get like a better handle on the error pass of the simulation. But this is in reasonable agreement, like the barrier is in good agreement, and there's some small differences here. But this is, I think, is all within like some, should be within error pass. So we can also now do again the rebating. This is again just rebating using kernel density estimator, but we're now doing this for the other simulation. It's just this, and now we plot the different result. So now here the dotted lines are the rebated result, the solid lines are the directly from the bias potential, and you can see that most of these runs directly from the bias and rebating are in good agreement with each other. So it's it's pretty reasonable agreement here in this case between the different runs. Okay, let's look again at the Fringe difference between the two states as before and compare it to what we got in the other independent run. And we can see, okay, they're not totally agree, but they are kind of should be kind of converging to similar results. So maybe if we would run them both longer, they would converge better. But this is like they are in reasonable agreement at the end. This is within, let's say, 0.1 kPa. So this difference is here around 0.3 kilojoule per mole. Okay, so now, so this was for another independent simulation. So now let's bias two collective variables. So let's bias also the other collective variable. So in this case, this is what they do here. So now we need to add another basis set. Let me see. That one is where is it? Exercise 4 here. So because the basis set has to be defined for a given range. So if you add another collective variable, you need to add a new basis set. In this case, so this is just the basis set for the distance. And now we add a basis set for the coordination number. So here we now also need to basically define the minimum and maximum. And this is something, this minimum maximum is something which we could have looked at, like the time series of the coordination number, how it behaved. So these here, minimum here, are a reasonable one. Everything is basically the same as before. We just need to basically add the basis function to the pairs linear expansion. And to note, when we're using like a two-dimensional basis set, we use a tensor product of one-dimensional basis functions. And now we just need to add a second grid for the like some internal calculations in this action here. And also just to assess the convergence, here we will also output projections on the different collective variables, because the pairs that we get directly would just be the two-dimensional pairs. But that one is sometimes difficult to kind of assess the convergence. So to assess the convergence, it's better to look at like one-dimensional profiles. So this is the keyword here, where it is turn on output of projections. In principle, you could do it afterwards in post-processing using some kind of Python code, but this is just convenient because then you get out these kind of projections. So if you look at this exercise 4, the run, so you get like these files here is the different pairs files. They're a bit large because these are like two-dimensional surfaces. But now here you have this projection 1, which is correspond to the first collective variable, and this projection 2, which is the other collective variable. So these are just one-dimensional profiles. And now if you look at the coefficient file, you can see there are much more coefficients, because now we have here like the indexes of the different Bayesian functions, because you have 2 indexes. So now we have like 26 times 26 coefficients. So this is basically all the coefficients. So we have much more coefficients in this case. So like we have in total 675 coefficients. So this is like how it would behave for the two-dimensional pairs. Okay. Now just look at the time series. We can see as before the distance is like diffusive as before. This is just the distance here. And now we can look at the solvation degree of freedom and how it behaves. And now maybe it's interesting to compare how the solvation degree of freedom, the time series looks like compared when we're not biasing in it and when we bias it. So in this case here, this blue is basically when we biased like only both the distance and solvation, and the orange and when we biased only the distance. As expecting, the solvation will explore more larger CV space because we are biasing this degree of freedom. So this is all reasonable. And this is just like looking at like how the CV space that we're exploring. As we're now biasing also the solvation, we explore much larger range of the CV space. But in general, we can see that we have here the good exploration in both degrees of freedom. So now let's look at the fringe surface. So now let's look at the projection on the distance. And so this is basically the projection on the distance as a function of time as before. And this is just, okay, there's some more fluctuation than we saw in the previous one. So maybe we might run it a bit longer. But this is from the beginning to the end. But if you look at the last nanosecond or last 1000 picosecond, there are some variations, but this is, I think, still is a reasonable kind of convergence. So maybe we should have run this more. In this case, we run it for 4000 picoseconds, but maybe we should have run it a bit longer. Okay, so this is then we can look at the projection of the solvation degree of freedom, and there, yeah. So we can see here that how this behaves. And this also is kind of a converging. This is reasonably converged. I mean, there's some differences. Okay, so this is like for this solvation degree of freedom. So now let's compare the fringe surface for the distance from different runs. This is one of the different runs. So basically, run one and 2 is this 2 independent simulation biasing only in the distance, and run 3 is biased in distance and solvation. And you can see they're mostly in agreement with each other. So then we can also do rebating on the distance. And as I say, it's always good practice to also do rebating to calculate the result. So here we just take this simulation where we're biasing 2 collective variables in this exercise 4 and do rebating for that. So this is just the same input as before. It's just that we rebate the simulation. And yes, so this is done. And here now we plot the different runs. So here the dotted lines are the derivative result, while the solid lines are the directly from the bias. So you can see they're all in a very similar ball range. They're all in similar, like similar within its range. They're all similar, like agree reasonably well with each other, which will indicate that everything is going fine with these simulations. And then we can also take this projections and look at the fringe difference as before. So this is just the same plot as before. We calculate the fringe difference now for exercise 4 and look at that. And here we can see that they, like this exercise run 1 and 3, which correspond to exercise 1 and 4, they are in good agreement, while this run exercise 3 is the other independent simulation, bias on only one run, is slightly higher. But as I say, these differences are in the order of 0.3 kilojoule or so. So this is a reasonable agreement. Probably if we would run further simulation, you would see that there is that they will all kind of spread slightly around this range here. Okay. So now so far we're biasing 2 collective variables, but so far we only looked at the 1-dimensional projections. And this is useful because it's difficult to assess convergence from the 2 dimensions. So here I'm just plotting the distance, the phase for the distance, and the solvation degree of freedom. And this is the phase here, and yeah, this is the phase directly from the bias potential, and this is in reasonable agreement with the phase that we got from rebating the previous simulation. There's some small differences, but this is a bit noisy because of the rebating. And if we look at, we can also just look at the 2-dimensional phase at different times. This is what we do here. And we can see that there are some small changes as a function of time, but within, let's say, from the first to the last, we don't see major differences, for example, unless maybe in this space in here. So this is why it's difficult to assess convergence from directly from the 2-dimensional phase. So it's better to look at the 1-dimensional projections. Okay, so finally there are 2. I did not do exercise 5, which was to play with the optimization parameter. This is something which one can do if one is interested. But what is, maybe I will do finally this optional 2 exercises, which is 6 and 7. And the first one is to look at if we use a uniform target distribution. Basically, so here in this case, we just need to change the target distribution from well-tempered to uniform. So this means that we aim to completely flatten the sampling. So that one is So basically in the Colvar file, in the plumed input file, you just change this keyword here. You don't really need to change anything else, but you also need to remove this keyword with the updating of the target distribution, because this is a fixed target distribution throughout. But the code will also complain if you make a mistake in the output, in the input, sorry. Okay, so this is just basically the time series. And again, we see very diffusive behavior. And actually, we don't see a large difference compared to the uniform and the well-tempered target distribution in the behavior here. It's difficult to assess. We probably should do a histogram of the sampling to assess, to understand this better. But that's not really, we'll not do that now. So now, again, we look at the convergence of the FAS. And in this case, we get pretty good convergence. This is like from the beginning. So just do the same as before, look at the convergence of the fringe surface. And now we look at the convergence over the last 1000 picoseconds. And you can see it converges pretty well. Yeah. And we can do the rebating as before and can compare to other results. So now we have here, we compare, let's say, with from the previous result. So here we have like run 1, which was using a well-tempered target distribution, compared to run 2, using a uniform target distribution. And we can see that they are in pretty good agreement. And also the related results are also in good agreement. So this all seems to be kind of, give reasonable result. And again, we can look at the fringe difference. And like we can see here, that's this run 4, which is exercise 6, is also in agreement with these 2 runs. And also it seems to converge slightly better. So this is all, like they're all kind of in a spread which is around 0.5 kilojoule per mole or something like that. It's around, 2.25 kpts or so. So this is, so the kind of conversion is quite nice. So finally, let's look at the so-called Ligand polynomials. So Ligand polynomials is the basic function that have been used so far until we introduced these wavelets more recently, and they are kind of delocalized basic functions. For further discussion, I will just refer to the paper introducing the wavelets. And one of the main conclusions from that paper is that the wavelets are more stable and fluctuate less. So the Ligand polynomials have more fluctuations. So here we just use the same exact parameters, except we change the basis set from like wavelets to Lagrangian. And this is this exercise 7. And here is the is basically the basis set for the distance. Here the order has a slightly different meaning than for the wavelets. The order is the highest order of the polynomials that we use. But okay, as I say, these are the localized, and you will see this that this behaves slightly worse. So here, this is just the time series. Looks good as before. Like we don't see any major differences. And now let's look at the fringe surface itself. Now we can see there are much more fluctuations in the bias potential. So it has slower convergence. Maybe in this case, it could also be, I did not test this extensively or did not test this. It might be that we might reduce the step size in this case to a lower number to get more stable results. So it might be that step size is not optimal for the Ligand polynomial in this case. So, and again, if you look at the last 10 nanoseconds, the is still fluctuating a bit. Now, okay, what about rebating? In this case, we can also do the rebating, and we trimmed like the first 500 as before, and we now plot here this result. We can see here that the result with the Lagrange polynomial there is not as good, but still the rebating results are in agreement with the previous result. So in this case, although the bias potential is not converging well, or the FAS, we could have gotten reasonable result by using rebating. So finally, that we look at is just to look at the fringe difference as before. And as you can see here for the Lagrange polynomial, which is this purple line here, 1.5, exercise 7, that this is fluctuating much more than the other ones. So, and this is in line what we saw in the behavior in the new paper, that the wavelets perform much better. So in this case, we can see how kind of it converges. One thing which I didn't mention is that here I only calculate the fringe difference from the bias directly from the fringe surface directly from the bias potential. But in principle, you could also calculate the fringe difference from the rebated FAS. You could create a new loop to do that, and that's also easy to do. Okay, let me see. So this is more or less kind of the solutions from this tutorial here. And yeah, so just some additional comments. It's very easy to restart via simulations, because at the end of the simulation, the code will automatically output all the files that are needed for the restart. So if you're doing a restart, you just need to restart the simulation using the empty code, like this normal way you restart your simulation. And this is easy. Chromax, for example, and in principle, you just need to add the restart keyword to indicate that you're restarting. But in some cases, like for Chromax, this is not needed anymore, because PLUMED will automatically detect that it's a restart. But this is something which one can easily do. Like in some of the cases, it might be good to run a bit longer, and this is easy to do. And yeah, also to kind of improve the convergence, it's also convenient to use multiple walkers, which are like multiple copies of the system that share the same bias potential. In other words, they share the same coefficients. So, and cooperatively sample the average needed for the gradient in Hessian. And this can improve convergence in some cases. And this is just can be done by using this, adding this multiple walkers keyword to the optimizer. And using empty code that supports multiple walkers. Some of the things which I did not talk about here, for example, which I mentioned in the lecture last time, was, for example, obtaining kinetics. And this I have not touched upon here, but in the VAS module, there's an old tutorial that discusses about a bit about that. So you could look into that tutorial if you're interested in like how to obtain kinetics from variational sampling. So maybe that tutorial should be updated slightly. So that one kind of completes kind of the solution which I wanted to talk about at this time. I've already uploaded the Jupyter notebook used in this runs to the GitHub, and I also did and also Jupyter notebook with all the solutions, and you can like see it here. And also I added all the runs from the there are all the runs included in the here. So all the files that I analyzed here are included. So yeah. So with that I would just like to end this kind of solutions. Or I don't have anything more to say about the solutions.
Okay, great. Thanks, Omar. So I don't know if there's any other question from Francisco.
Okay, thank you.
Yeah, thank you.
So if not, then thank again, Omar.
Yeah, thank you.
And yeah, and thanks to everyone